We've built a neuron and we've given it a bend so it can learn curves, but we keep using one word without explaining it: learning. Before a network can get better, it needs to know how wrong it is right now as a single hard number. That number is the loss, it's the compass for everything that follows. Start with one example. The model looks at a house and predicts a price, say 3.2. The real price was 5.0, so it's wrong, and it's wrong by 1.8. That gap between what the model said and what was actually true is the raw material of learning. The loss function's job is to turn that gap into a score. A loss function takes the prediction and the true answer and returns a single number. How bad was this? A big number means very wrong, 0 means perfect, and that flips the entire problem on its head. Suddenly, make the model good becomes something precise. Make this number as small as possible. All of training is just one relentless goal: drive the loss down. For predicting numbers, the workhorse is mean squared error. For each example, take the gap between prediction and target and square it. Then average that over all your examples. Square, then average. That single number is the model's total wrongness across the whole dataset, and it's what we'll try to shrink. But why square the gap? 3 reasons, all clever. First, squaring makes every error positive, so overshooting and undershooting both count as wrong. They can't cancel out. Second, it punishes big mistakes far more than small ones. An error of 2 isn't twice as bad, it's 4 times as bad. And third, the squared curve is smooth, and that smoothness is exactly what lets us do calculus on it later. Here's the picture to keep in your head. As you change the model's weights, the loss goes up and down, tracing out a surface. With squared error, that surface is a smooth bowl. High loss up on the walls, low loss down in the valley. Every possible setting of the weights is a point on that surface, and the height at that point is how wrong the model would be. Training is nothing more than rolling that ball downhill to the bottom of the bowl to the weights that make the loss as small as it can be. How we roll it is a whole episode of its own, but the bowl is what we're rolling down. Now, squared error is perfect for predicting numbers, but a lot of the time we're not predicting a number, we're predicting a category, cat or dog, spam or not, and there the model outputs a probability. I am 70% sure it's a cat. Measuring wrongness for a probability needs a different, sharper tool. You could still use squared error on probabilities, but it's weak. When the model is confidently, catastrophically wrong, squared error only nudges it a little. We want the opposite, a loss that screams when the model is sure and wrong. We want confidence in a wrong answer to be punished hard. That tool is cross-entropy. The idea is beautifully simple. Look only at the probability the model gave to the correct answer and take the negative logarithm of it. If the model put high probability on the right class, that's a small loss. If it put low probability on the right class, the loss explodes. It measures surprise, how shocked the model should be by the truth. The more confident the model was in the wrong direction, the more surprised it should be, and the bigger the penalty it pays. Look at the negative log curve. When the probability of the true class is near 1, the model was confident and right, the loss is almost 0. But as that probability drops towards 0, confident and wrong, the loss shoots up toward infinity. That steep wall is the whole point. It makes being sure and wrong the most expensive mistake a model can make. When there are only 2 choices, yes or no, this simplifies to binary cross-entropy. One probability P for yes. If the truth is yes, the loss is negative log of P. If the truth is no, it's negative log of 1 minus P. Same idea, just the 2 outcome version. And it's behind almost every yes or no model you'll ever train. Step back. Whatever loss you pick, squared error for numbers, cross-entropy for categories, You compute it for every example and average it into one final number. That average is the model's report card. And a good loss has one more quiet superpower. It's smooth and differentiable, which means we can measure which way is downhill. So that's the loss, a single number that captures how wrong the model is, built to punish the right kinds of mistakes. It's the target, it's the compass, but a compass only tells you which way is bad, it doesn't move you. Next episode, we answer the real question. Given the loss, how does the network actually change its weights to make it smaller? That's gradient descent. See you there.